I present NeuralEditor, editing neural Radiance fields via manipulated point clouds. Shape editing of things impacts many applications in computer vision industry. The main objective of this task is to generate visually faithful results consistent with the ambient environment. Previous work renders deformed scene by deforming rays, which only supports coarse-grained mild continuous deformations and fails in challenging tasks as shown below. Moreover, these methods are only designed for shape deformation, on specific tasks of scene editing, and do not support fine-tuning. We propose our NeuralEditor, a unified method for all shape editing tasks including shape deformation and more challenging scene morphing, and supports fine-tuning towards better consistency. The key insight of this paper is as follows. Implicit scene representation like nerve render good results but does not support scene editing, while explicit representation like point cloud natively allows shape editing. Observing that nerve rendering is equivalent to plotting a point cloud, we integrate the nerve and point cloud for both advantages. Point cloud guided nerve. We propose an input point cloud guided nerve that supports scene editing by directly manipulating its point cloud. To fit our need of shape editing, we propose our input point cloud guided nerve on top of point nerve, with better point cloud organization, rendering scheme, shape optimization, and color modeling. With these improvements, we are able to propose a unified scheme of general shape editing. Nerve requires data structure to skip empty space and focus on crucial parts, where point nerve uses a single-scale method to construct bounding boxes. As an improvement, we use KD tree to produce multi-scale bounding boxes, or voxels. Each layer represents a scale, making a top-down process of the tree a native cost-to-find approximation of the shape. We render over the KD tree guided voxels by only sampling in the voxels at layer via top-down recursion, which implicitly applies a cost-to-find rendering. As such rendering scheme guarantees the complexity upper bound of each voxel, we propose a deterministic spline integration rendering scheme. We firstly uniform sample points on an intersecting segment, calculating their embeddings, and do a spline integration to calculate the average embedding as the embedding of a representative sampled points in the rendering formula. Such deterministic scheme is efficient and stable without random sampling and accounts for the embeddings of the whole segment. We also model norms for better shape utilization. There are two ways to calculate the norm: to estimate from the nearest neighbors of the point cloud, or to calculate by the gradient of the volume density of nerve. We regularize these two estimations to be the same to prune the outliers with abnormal norms. By engaging norm within the training process, we provide more clues of optimizing the shape and potentially lead to a precise point cloud. We further utilize the norms for color modeling by using phone reflection. Observing that specular is a function of reflection of viewing direction by a norm, we model the view dependence color as a function of such reflection. We also model other attributes like reflection and shyness constants to achieve better color modeling and decomposition and norm utilization. With the input point cloud nerve, we define the unified shape editing with an indexed point cloud. We define a point cloud being a mapping from index to point, and a scene operation as another point cloud with the same set of indexes, meaning that a point of each index moves to the new given location. Such definition is general with minimum extra information, without any assumption of smoothness, continuity, or modelability. It covers the shape deformation task, and even the scene morphing task never studied by the previous work. We apply such scene editing on our input nerve by directly replacing the point cloud. The edited nerve is still valid and fully functional, and therefore supports fine-tuning. In our experiments, our NeuralEditor renders high-quality results in both shape deformation as shown on the left, and scene morphing task as shown on the right. On the left, we can see that we support non-continuous shape editing, like in the Lego scene. And on the right part is a recurrent scene morphing from hot dog to Lego to Mike and now to chair, and last back to hot dog. In the quantitative benchmark constructed by us, our NeuralEditor significantly outperforms baselines and clearly further improves consistency after fine-tuning. The qualitative results on our dataset also show that our NeuralEditor renders more realistic results than point-nerf in the shape deformation task. Our NeuralEditor even supports scene morphing that never studied or supported by all the previous work. Also, we render better results than point-nerf, which contain blur textures, shadows, and gloomy non-smooth colors, while our NeuralEditor always renders with clear texture and bright colors. Our ablation study shows that all our design choice, including deterministic spline integration rendering scheme, surface norms for better shape utilization, and phone reflection color modeling, benefit our rendering results, while removing any of them still clearly outperforms point-nerf. Note that some of the design choices do not show a high improvement in the zero-shot inference. However, in the fine-tuned scheme, the performance severely drops after removing them. This shows that these designs also highly benefits the fast fitting towards ambient consistency. As a conclusion, in this paper, we propose our novel NeuralEditor that enables general shape editing on Nerf in a unified way. Our NeuralEditor renders high-quality and visually faithful results in both shape deformation task and the scene morphing task never studied by the previous work. We also constructed a novel benchmark for shape deformation task. Thank you very much for listening. Please visit our project page and poster session for more information about NeuralEditor.